Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 21, merge two sorted lists. After that, we'll go over two actual variants of the original question that Meta asks. They're both very similar to one another, but drastically different from the OG problem. What if you were given three lists and they weren't linked lists? But anyway, enough talking, let's get into the problem. Okay, so we're given the head nodes of two linked lists, list 1 and list 2. Here in our example, here's the head node of list 1 and the head node of list 2. I've abbreviated list 1 as L1 and list 2 as L2 for short. Moreover, the two input linked lists are sorted by their integer values in non-decreasing order. So take L1 for example, we go from 3 to the 10, 10 to node 10, and yes, just so you know, a non-decreasing order just means the next node can have the same value or higher. That can happen, it's not too important of a detail. But anyway, lastly, we go from node 10 to node 12. Our goal is relatively straightforward. We want to merge the two lists into one sorted list. Let me redirect your attention. LeetCode actually has a helpful visual here. Here are the two sorted lists, L1 and L2. And here's the result after we've combined the two into a mega list that is also sorted in non-decreasing order. As you can see, the combined list first takes list 2's node of 1, and then list 1's node of 1, the 2, 3, 4, and lastly another 4. We'll ultimately return the head node of the merge linked list. So in regards to LeetCode's first example, it would be this node. Great, but how do we approach the problem? Well, taking another gander at the problem description, it also says that we have to splice together the nodes of the two linked lists. That's another way of saying we need to do the merging in place. And with linked list nodes means we have to reassign the next pointer field to the subsequent node, specifically of the node that has the next higher number. So 6 to 8, 8 to 10. Next up here, you have two duplicate 10s. It doesn't matter which one we pick. Sure, let's go for list 1's 10, 10 to another 10, this 10 to node 12, and finally node 12 to 13. That sounds like fine logic to me, but what are the implications for the very first node, node 3 in this example? There's no existing node before to set its next pointer to the initial node, node 3. Therefore, it only makes sense to create a dummy node. It doesn't matter what value it has. Let's go with -1 and name it C, which stands for current, as in the current node. All this to say, when we find the first node of our merged answer, we'll set the current node's next node as appropriate. And once we're done with the whole workflow, like we just demonstrated here, we can simply return the current node's next pointer, which is this right here, as the answer. Again, that would be the head of the merge linked list. You may be wondering why we need to do all this to begin with, but trust me, it helps with very annoying edge cases. I'd rather not have references to both head nodes and return the one that's lower at the end of our whole workflow. But also we could be given head nodes that point to nothing, to null pointer, in which case we need if statements for that as well. A dummy node is just a more concise technique. Okay, so that's the general idea, but how do we actually find the right nodes in the sorted order? Recall a very important detail. Each list is sorted within its own list, meaning L1 of list 1 points to the lowest value in its list, and L2 of list 2 points to the lowest value in its list. Therefore, we can use the two given head nodes L1 and L2 and enter a while loop that as long as both are in bounds and refer to a node, then we can have an if statement to check for the lower value between the two. Here, between 3 and 6, it's obviously 3. And once we've found the next higher valued node, we'll slowly build our merged linked lists. Remember, we can simply assign the next pointer of the current node to the 3. But actually, I'm instead going to draw node 3 down here. Don't be confused, this is the same exact node as this one. I'm just drawing it down here visually, just so things don't get too cluttered up here. Now that we've done that, let's progress all of our pointers as necessary to ready for the next iteration of our while loop. But which ones? Well, since we used the node that L1 pointed to, let's progress it to the next node, node 10. We do not change what L2 points to because we didn't use the 6 in our merge result yet. Okay, what about the current node? Well, the current node should point to the next node to keep building our answer. That whenever we do find the next higher valued node, we'll set its next pointer to whatever that node is. Okay, so we've ironed out some details of our loop. Let's move on to the next iteration and repeat this logic. Let's make that if statement check which node is lower, 6 or 10. It's the 6. Let's set the current node's next field to node 6 in list 2. This means we used up node 6, so let's move L2 to its next node, 8. Lastly, we'll progress our current pointer and we move on. Next up, as we can see, L1 and L2 still point to nodes, so they're both considered inbounds and we keep iterating. What do we do first? Our if statement deems that between these two numbers, 8 is obviously lower, so we'll set the current node's next pointer to that node 8. As per usual, let's move ahead L2 as well as our current node. So far so good, everything in our merge result is in order. On the next iteration, we can see that L1 and L2 both point to duplicate values 10. What do we do here? Well, it doesn't matter which node 10 we pick, because whatever node 10 we don't pick, we'll pick it on the next iteration. In our code, you'll see that we arbitrarily pick L1's node if both nodes are equal. Great, so let's set it as per usual to list 1's node and progress that pointer forwards. As always, move ahead our current node. On the next iteration, you see you also have another duplicate, 10 and 10. Remember, we bias towards list 1, so let's set that as such. Move along L1 as well as the current node. Afterwards, on the next iteration, which node is lower, 10 or the 12? The 10, let's set it. Progress L2 and move the current node. You kind of get the idea at this point. On the next iteration, L1 and L2 still points to nodes, so no null pointer just yet. Which value is lower, 12 or 13? It's the 12 in list 1. Let's set that. And because we use the 12, let's move L1 and our current node. And now we stop our while loop because L1 no longer points to a node. Every node in list 1 was indeed exhausted. However, in doing so, we realize we have a node left over in our other list, list 2, namely this 13. And just a quick note, the two linked lists don't necessarily need to have the same number of nodes. There could have been a node 15 for all we knew, and then a node 90, whatever. Either way, we obviously want to include the leftover node or nodes in our merge result. To remedy this, after our main while loop, we can have an if statement check to see which list still has nodes to be appended. Here it's the L2. We'll do one last manual set to L2 in this example. And there you have it. This is looking like our answer. You can, if you want, progress L2 one last time, but it doesn't matter because we've technically used all the nodes between the two lists. All right, let's wrap up and return the head node of our merge linked list. But wait 1 second, we've lost all references to our initial dummy node. The current node is all the way over here. We can't access the node we want to return, node 3. Therefore, when we created our dummy node before our while loop, we'll actually save another reference to it in a variable called head. It stays put as our current pointer progresses as normal. And when we're done with the entire workflow, we'll have the pointer necessary to return the head of our merged linked list. Head next would refer to this 3, that's what we return, and that's our answer. The time complexity is big O m plus n, where m is the length of list 1 and n the length of list 2. The space complexity is big O1 because we didn't use any external storage other than the single dummy node. Okay, awesome. Let's code this up. The first thing we'll do is initiate our dummy node. Remember, we called it C for the current node and defaulted its value to -1. The -1 is arbitrary. We won't use it for anything. Next, we'll save a reference to this node called head because we'll eventually return its next node as the answer of our merged list. The last thing I'll do before we start our main while loop is write some syntactic sugar. Remember, in the diagram, we use L1 for list 1 and L2 for list 2. You don't have to do this. I'm just doing it to be consistent with the visual before. Now we can finally enter our while loop. And remember, we keep going as long as L1 doesn't point to a null pointer, and the same deal with L2. What do we do on each iteration? Well, we find out which value is lower between our two pointers. And in the case that L1's value is lower or equal, because remember, we bias towards list 1 in the case where we have duplicate values, then we'll set the current node's next pointer to L1. Of course, we'll progress L1 forward because we used that value. Otherwise, in the case where L2 is lower, then we'll set the current node's next pointer to L2 and similarly progress L2 forwards. The last thing we'll do in any given iteration is move the current node forward to ready ourselves for the next iteration. Now, when that main while loop is all said and done, we need one last if statement to check which pointer points to the leftover node that we have to append. So what about in the case where L1 still has nodes that we have to append? Well, let's do one last manual set. Currents next will equal to L1. Otherwise, if L2 still has nodes, then we'll set the currents next to L2. And that is really it. Okay, you'll see that the variant is quite different. Let's get started. If you were asked the original LeetCode problem, then consider yourself lucky. The variant is doable, but it would be tricky to solve in 15 minutes time if you've never seen it before. Okay, let's get started. We're given 3 lists of integers, namely list A, list B, and list C. Looking at our examples here they are. And just like before, all the values in each list are sorted in non-decreasing order. So for example, list A goes from 2 to 4, 4 to 5, 5 to 5, and lastly 5 to 6. And yes, non-decreasing would mean that we can have duplicates such as these two 5s. Our goal is to merge the 3 lists into a single sorted list and return it. Furthermore, we're given another restraint. We can only use auxiliary space to return our answer. Okay, so what's the intuition here? Well, unlike before, we're given vectors of numbers, not linked lists. Therefore, we have the luxury of looping through 2 lists, say list A and list B, and add all those values to our third list, list C. And now that they're all in one singular list, then we can use an inbuilt sort function to sort all of them in non-decreasing order. Our resulting list, which again is the auxiliary space, would consist of the 1, 2, 3, 2 4s, 2 5s, a 6, and a 7. But just because we can do this doesn't mean we should. The time complexity comes out to be A plus B plus C log A plus B plus C, because we're sorting across all these 3 lists. And Meta or any big tech company won't accept this solution. What do? We can carry some of the same ideas inspired from the original LeetCode problem. Before, we realized we used a 2-pointer approach because we were given 2 sorted lists. Sure, linked lists, but they were still lists. Why not here use a 3-pointer approach now that we're given 3 sorted lists? We can have a pointer, sure, called A for list A, B for list B, and C for list C. That makes sense to me. Secondly, similar to before, we can enter a main while loop as long as all 3 pointers point to a value, or in other words, are in bounds of their respective lists. Furthermore, on each iteration of our while loop, we'll determine which one is the minimum value to add to our resulting list. Let's call it that, result. And by finding the minimum value on each iteration, we'll be able to process each integer from the lowest to the highest, and thus a non-decreasing order. So on the first iteration, what's the minimum value here? A points at 2, B at 1, and C at 4. It's clearly the 1, so let's push it to our result. And since we used up this 1 here, let's increment its pointer B to the next index, very much like how we set a node pointer to its next node in the previous problem. But how do we do this in code? We'll have a series of if statements to check which pointer pointed to the 1. Going down the list from top bottom, it's not the A because it points at 2, but it is the B because it points at the 1. And that's how we'll decide to increment the B pointer. Alright, now we repeat the logic on the next iteration of our loop. All 3 pointers are still in bounds. That's fantastic. What is our minimum value? Is it 2, 3, or 4? It's the 2 in list A, so let's push that to our result. And since we processed the 2, let's enter our gauntlet of 3 if statements. Was the 2 found in list A? Yup, let's move that ahead then. On the next iteration, what's the minimum value? 4, 3, or another 4? It's quite obviously the 3. Let's push it into our answer. Increment B. And just like that, we stop our while loop because B is at an index no longer in list B. Now, do we mimic our code in the original LeetCode problem and loop through the remaining lists that still have values, A and C, and blindly append them to our answer? Well, we can try. I'm unsure of which list to add first, but sure, YOLO, let's start with list A and add its leftover unprocessed values. We have a 4, 5, 5, and then 6. Now let's add the leftover values in list C, like so, 4 and 7. We notice, however, that our resulting list is not sorted in non-decreasing order. For one, we'd like this 4 to be somewhere before the 5s. This is not right. Now, even if we did it the other way around and added everything in list C first, like so, the 4, 7, and then from list A, 4, 5, 5, 6, we still wouldn't have the desired order. For example, 4 needs to be before the 7 and the 7 at the very end, after the 6. Ideally, what we did was next process this 4, and then this 4 in list C, and then the 2 5s in list A, as well as its 6, and then lastly, the 7 in list C. This makes us realize that we need to process the remaining values in the same way we did in our main while loop, and bounce from list to list for the next minimum value, even if a pointer is out of bounds. That's the key observation. Thusly, the first revision we make to our algorithm is to keep looping as long as at least one pointer is in bounds and pointing to an integer. Here, we have A to 4 and C points to another 4. We can keep going. Okay, so let's start from this iteration where we were before we went down that rabbit hole. Pointer B had newly exhausted all of its elements. It's out of bounds. How do we get the minimum number without accessing an out of bounds and exploding our code? Well, if a pointer like B is indeed outside its array, why not default its value to an arbitrarily high number like int max? Looking at our restraints right here, the upper bound of any number is up to 1000, meaning we're guaranteed to never accidentally push the int max, a value of 2 billion or something, into our resulting vector. The values in the other two lists, the 4 and 4 in this case, will always be lower and thus be chosen over the 2 billion. Okay, let's move forward. What's the smallest number? 4, 2 billion, or another 4? It's a 4. Let's push it. But hold on one second, there are duplicates. List A had a 4, list C had a 4, both of which were minimum values. In our series of if statements to progress a pointer, which pointer do we increment? It actually doesn't matter. If we incremented A, then you'll see that on the next iteration, we'll process the 4 from list C. And if we incremented C, then you'll see on the next iteration, we add the 4 from list A. The outcome is the same. And since the order is arbitrary, it doesn't matter which list we pick first. All to say, our gauntlet of if statements to firstly check list A, and then B, and lastly C will still work. Okay, so going through that logic, does pointer A point to our minimum value of 4? Yes, it does. Let's increment it. On the next iteration, at least one pointer is still in bounds. We can keep going. What's the minimum value here? 5, 2 billion, or 4. It's the 4 from list C. Let's push it to our answer of a 4 and increment its index. After that, we repeat the logic. What's the lowest? 5, 2 billion, or a 7. It's the 5 from list A. Let's push it into our result and increment A. On the next iteration, A points at 5, B at 2 billion, and C at 7. The minimum value is the 5 yet again from list A. Let's increment its pointer. And similarly, 6 is the next minimum value. Let's really quick add that and increment A. On the next iteration, we note that at least one pointer is still in bounds. It's the C here to point at the 7, so we still have values to process. Let's compare the three numbers. A is now out of bounds, so it'll be defaulted to int max, a very high number. So looking at it, it can't be more obvious what's the smaller value, int max, or A7. It's the 7, let's add it there and increment C. And we've hit our base case, not a single pointer is now in bounds. That means we've exhausted every single number, and our result now has the non-decreasing order we wanted. The time complexity has really improved to A plus B plus C because we process every element once. The space complexity remains to be big O1, unless of course you want to count the auxiliary space of the result, in which case it's big O(n). Very cool, let's implement this now. The first thing we observe is that our signature changes. It's now called merge 3 lists, and we're given 3 lists of numbers rather than 2 linked lists of numbers. After that, we'll do the one fun thing and demolish the old code. We are no longer working with linked lists. First order of business, let's initialize our resulting vector of numbers. And let's return it at the very end because I easily forget things. Next up, let's write up all 3 pointers. Recall that we named them A, B, and C respectively. And now we can enter our while loop. Our while loop will go on as long as at least one pointer is in bounds. So A can be in bounds, or B can be in bounds, or lastly C can be in bounds. If this is the case, that must mean there's at least one value left to process. Let's figure out the minimum value. Let's figure out the value for A first. Now we're very scared of out-of-bound errors, so let's have a conditional that if A is still in bounds, then we'll return whatever value is there. Otherwise, it's out of bounds. Let's default it to the int max. We will do very similar things for the other 3 pointers. This is technically very redundant code, but it's okay because we're only ever given 3 lists and 3 lists only. Beyond this, you would obviously need some sort of automation. If C is in bounds, we'll return whatever is at the C pointer. Otherwise, we default to 2 billion. Great, with lines 9 through 11, let's figure out the minimum value, which obviously is the minimum between the value at A, B, and C. They could be 2 billion, but we never choose it. The highest value any number can take on in this example is 1,000. After we found the minimum value, let's push it into our result. Min val. Last thing we'll do is increment the pointer that pointed to that minimum value on line 13. Remember, we opt to check if the minimum value is equal to the A value first, and if it does, we'll increment A. Otherwise, if the B value equals the minimum value, then we'll similarly increment B. Otherwise, it must be equal to the C value. We'll increment it like so. You can do any order you want. We just chose A to B to C because it makes more sense in my head. All right, and that's the entirety of the code. It's not too bad. Now let's move on to the second variant. Variant 2 is short and sweet, but only because it builds off the previous variant. Therefore, we'll be reusing that code implementation as a starting template. As it turns out, all of the requirements remain the same except for one change. Check out this sentence right here. We have to merge the 3 lists into a single sorted list, but without duplicates. We still want values in our result in non-decreasing order, but now all the integers in our answer must be unique, like so. We can't have multiple 4s, for example, or 6s, so forth. Alright, so let's approach this variant a bit differently. Let's pretend we're developers at our everyday 9-to-5 job, and that with this new feature requirement, or more accurately a constraint, let's look at our codebase, which from the first variant consisted of a single function, and see what functionality we may need to modify or extend. Okay, so summarizing the workflow of our tiny codebase, we enter a while loop that can be logically explained in 3 parts. 1, we determine the value at each pointer. And remember, we set it to an arbitrarily high number in the case that the pointer is out of bounds of its respective list. 2, we determine the minimum value among those 3 values and push it to our resulting vector. Thirdly, and lastly, we'll increment the pointer whose value was the minimum value we had just found. Now, our new constraint is that we cannot have duplicate values when we push the next minimum value. So which part do we modify? Part 1, Part 2, or Part 3? Sorry, this is starting to sound like a Dora the Explorer episode because it's very obvious we want to modify Part 2 with this associated logic. But how exactly? Let's debug our code with a contrived example to figure this out. On the first iteration, what's the minimum value among these 3 pointers? Is it 1, 1, or 2? It's obviously a 1. We want to proactively avoid duplicates, so why not check our result to see if it already had a 1? That makes sense to me. But here, no it doesn't, and that's because it's empty. There's literally no number to compare with yet. This is the first iteration. Intuitively, let's write an if statement for this. That if our result is empty, then there is no possibility of a duplicate yet. If this is the case, let's push the value to our result. Let's push the 1 like so, and as per usual, we'll increment the a pointer. Let's keep going in our example here and see if there's anything else we have to change. On our next iteration, we notice a is out of bounds, therefore it'll be defaulted to int max. And now we can compare the 3 values. What's the smallest? Is it 2 billion, 1, or 2? It's obviously the 1 from list B. We do not want duplicates. This 1 is a duplicate of the 1 in our answer so far. Does our current implementation work? Yes, it does, because as is, we only push when the result is empty. And here, clearly, it's not. It has a 1. Fantastic. Remember to increment B, and we move on to the next iteration. On this iteration, what's the minimum value? Is it 2 billion, 2, or another 2? It's a 2. A2 is clearly not a duplicate since we only have a 1 so far in our answer. We want to add the 2, but our code doesn't accommodate for this. Thus, let's extend this if statement that if our result vector is empty or the most recent value in our result is not equal to the current minimum we just found, then it must be unique. Let's push it. And indeed, obviously the 2 was not ever equal to 1. Fantastic. We now have 1, 2 in non-decreasing order. Don't forget to increment B. And whoops, it seems like I never initialized the C pointer. Let's pretend that was always there. On the last iteration, what is the minimum value? Is it 2 billion? Well, B points at 2 billion as well, because it's out of bounds. Or the 2. It's quite obviously the 2. Looking at our if statement here, the 2 is a duplicate because 2 equals the 2 in our result. We do not push it. We increment the C, and we've exhausted every single element. Our answer is 1, 2. There are no duplicates in sight. And that's it. We just introduced new code that accommodates a new constraint in our system. We collect our paycheck on the way out, and we are very satisfied with ourselves. Needless to say, the time complexity remains the same at A plus B plus C, and the space complexity is big O1. Great, I hope that made sense. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.